Another lecture of thermal engineering. Today we will discuss about multi-stage reaction turbines. So in the case of multi-stage reaction turbine, the steam leaving from the first moving blade is made to flow through fixed ring, and again it is made to strike on second moving blade. Now it completes two stages. After leaving second moving blade, it is again made to flow through fixed ring, and again it is made to strike on third moving blade. Now it completes three stages. So this process continues. The steam flows over the fixed blade first, then over the moving blade, then again fixed blade, moving blade. So one stage consists of a pair of fixed blade and a moving blade. Now the advantage why we go for multi-staging of reaction turbines is to make the pressure drop by stages, so that the load on the load on the reaction turbine can be reduced. Now here we can discuss a term called reheat factor. Reheat factor we will discuss in detail in the next slide. It is the ratio of cumulative heat drop to the isentropic heat drop. We will see what it is, what the cumulative heat drop is, and what is the isentropic heat drop. We will see in the next slides. Okay, what you are seeing is an HS graph, that is an specific enthalpy is drawn on the vertical axis, and the specific entropy is drawn on the horizontal axis. So, and the thick line, this thick line is the saturation curve. Whatever the condition of steam above this thick line is the superheated condition, over the thick line is the dry saturated condition, and below the thick line is the below the saturation, or the dark line is the this dark line is the wet steam condition. So at present, starting here you can see numbering 1. This is the initial stage of the steam while entering the steam turbine. Now in this diagram is for a 4 stage reaction turbine. So in between each stages there is an there will be intermediate pressure values. Now when the steam enters the turbine, the pressure is P1. So corresponding to P1, we can draw a isobar or the constant pressure line in the HS diagram like this curved line. Okay, now below that you can see P2. This is a intermediate pressure after stage 1. P3, it is another intermediate pressure after stage 2. P4 is the intermediate pressure after stage 3, and P5 is the intermediate pressure after stage 4. You can see this written clearly over here. The exit pressure of steam, P2 exit pressure of steam at stage 1, stage 2 is the P3, stage 4 is P4, and stage 5 is stage 4 is P5. Okay, now we can see some other notations like 2 dash, 3 dash, 4 dash, 5 dash. Now suppose we consider it the expansion of steam is ideal in the case of a reaction turbine, then it follows the isentropic condition, that is from 1 to 2 it will drop a vertical line. So the expansion of steam will be in this vertical line, but in actually that is not, it is not isentropic, it will be adiabatic. So it should follow the deviation line, that is 1 to 2 dash. So 2 dash will be the actual condition of steam after stage 1. Now when it enters stage 2, and if we assume that it follows the isentropic path, then it reaches 3, but actually in actual case the condition will be 3 dash, and in the next stage corresponding to the 3 over here we get 4, and in the last stage 5. Now if we consider the expansion in the turbine in a single stage, that is from the P1 pressure to P5 pressure, the expansion is taking place in a single stage, then we draw the ideal expansion line like this. From 1 to 6 a vertical line is dropped from 1 to 6. If the expansion is not taking place in multi-stages, if it is taking place in single stage, then it is from 1 to 6. And corresponding to this expansion, that is from 1 to 6, we have a ideal actual expansion, and that line is 1 5 dash 1 5 dash. Okay, now we can discuss about few terms relating to multi-stage turbines. First is the reheat factor, that is the cumulative heat drop to the isentropic heat drop. So cumulative heat drop we can calculate like this: H1 minus H2 plus H2 dash minus H3 plus H3 dash minus H4 plus H4 dash minus H5 divided by the total isentropic heat drop H1 minus H6. Now we can find the stage efficiency of multi-stage turbine, that is the useful enthalpy drop in one stage divided by the isentropic enthalpy drop for same stage, that is for the first stage H1 minus H2 dash divided by H1 minus H2. So the first stage efficiency will be same as the second stage efficiency. In the second stage, actual enthalpy, the enthalpy at the initial of starting of the second stage is 2 dash, and also in the case of isentropic also it is 2 dash, but after the expansion in the actual case it will become 3 dash, H3 dash. In the isentropic it is be H3, and so on. Now next efficiency is the internal or the isentropic efficiency or the overall turbine efficiency, that we calculate like this, that is H1 minus H2 dash plus H2 dash minus H3 dash, and so on. So if we add all these things, we get like this: H1 minus H5 dash divided by H1 minus H6. Now one more efficiency is there, that is the overall efficiency that we calculate, that is the ratio of total useful enthalpy drop to the heat supplied. We calculate like this: H1 minus H2 dash plus H2 dash minus H3 dash plus H3 dash minus H4 dash plus H4 dash minus H5 dash divided by H1 minus HF. HF is the enthalpy of the liquid condition after the condensation process. Now we have got another efficiency, that is the Rankine efficiency, isentropic enthalpy drop divided by the heat supply, H1 minus H6 divided by H1 minus HF. Okay, thank you.